For decades, the relational database has been the undisputed foundation of enterprise architecture. Systems like Postgres and SQL Server excel at storing structured data across perfectly defined tables, rows, and columns. To retrieve that data, these systems rely on exact matching. When you write a SQL query with a where clause, you are asking the database to find specific IDs, numeric thresholds, or exact keyword strings. But look at this split screen. On the left, a standard SQL query searches for the word rebate. It successfully pulls the first record. However, it completely fails to retrieve the second record. Dealer incentive settlement is still pending, even though any human immediately recognizes these two statements are describing the exact same business problem. This failure happens because relational systems process characters, not concepts. They do not understand linguistic variation, synonyms, or contextual intent. If we want to build artificial intelligence systems capable of parsing thousands of process documents, meeting transcripts, and complex requirements, enterprise data architecture must evolve to retrieve information based on actual meaning. Bridging this gap requires a system that treats language as geometry. A vector database uses high-dimensional mathematics to measure the distance between different concepts. This enables semantic search. Instead of looking for identical text characters, the system retrieves data based on intent and context, returning highly relevant information even when the exact words differ. Deploying this capability is a matter of software architecture rather than specialized hardware. It can be integrated into current relational infrastructures using commodity server resources.
To understand how this works in practice, we need to break down the mechanics of vector embeddings, explore how they integrate natively with relational systems, and calculate the precise hardware sizing required to run them. Adding vector functionality provides a persistent memory layer for modern AI systems, extending the utility of the structured data already stored in SQL. The first step in a semantic architecture requires an embedding model. These models take an unstructured chunk of text and translate it into a numerical format. You can see how this works on screen. The text "dealer rebate payment issue" transforms into a vector embedding, a long, high-dimensional array consisting of hundreds of floating point numbers. This sequence of numbers captures the deep semantic features of the original text. That entire array collapses into a single coordinate, which the database plots into a high-dimensional mathematical space. When we process thousands of enterprise documents through the same embedding model, a pattern emerges. Conceptually related items, like all discussions about payment processing, map to the exact same mathematical neighborhood, forming distinct spatial clusters. To find information, the vector database executes an approximate nearest neighbor, or ANN, search. When you ask an AI a question, that prompt is also converted into a coordinate. The ANN algorithm then uses metrics like cosine similarity or Euclidean distance to measure the physical gap between your question and the stored data, instantly pulling the closest points. Mapping concepts into physical spatial distances is the mechanism that allows a large language model to query vast archives of company knowledge without forcing you to load thousands of documents into its active prompt window. Traditional SQL and vector databases serve different primary goals. SQL guarantees precise data retrieval and secure, ACID-compliant transactions. Vector databases deliver contextual similarity. To combine these capabilities, enterprise architects generally choose between two deployment patterns. The first is a dedicated vector system, like Quadrant or Milvus. These are standalone, distributed databases built specifically for handling hundreds of millions of vectors at massive scale. The second pattern is the hybrid extension. This flowchart maps out a unified architecture using an open-source extension like pgvector for PostgreSQL. Notice how both the structured data branch and the unstructured document branch merge into a single database system.
This creates immediate architectural efficiency. Inside the unified database, you can store your user authentication, standard metadata, and the mathematical vector embeddings directly alongside one another in the exact same relational table. This means you can execute a single query that filters for a precise metadata match, like documents created in Q3, while simultaneously ordering the results by vector proximity to find the most relevant paragraphs. The output from this hybrid query is passed directly to the LLM. This precise retrieval loop is the foundational architecture for Retrieval Augmented Generation, or RAG. For most enterprise projects, a hybrid relational database provides full AI capabilities while avoiding the security liabilities of running two separate database platforms. There is a pervasive assumption in IT that running an enterprise AI database demands an array of expensive GPU supercomputers. The math proves otherwise. As this data pipeline shows, the hardware requirements split into two specific phases. Creating the embeddings from text does benefit heavily from GPU acceleration. However, once those vectors are stored, searching them is almost exclusively an operation bound by CPU and RAM. The RAM requirement for vector storage is calculated using a strict formula: the number of vectors, multiplied by the dimensions of the model, multiplied by the bytes per dimension, plus the memory overhead for the search index. Let's apply this to a standard embedding model that outputs 768 dimensions using 32-bit floats, which are 4 bytes each. The raw size of one vector is 768 times 4, coming out to roughly 3 kilobytes. Look at how this scales in the table below. Even if you process a corporate knowledge base of 1 million document chunks, the raw vector data requires roughly 3 gigabytes of memory. While advanced algorithms like HNSW indexes will add memory overhead to maintain search speed, the total footprint for 1 million vectors easily fits within the standard SSD and RAM configurations found on a developer's laptop or a small virtual machine. Calculating this math directly frees engineering teams from cloud cost anxiety. Production vector search is lightweight, highly accessible, and runs efficiently on standard enterprise hardware. When we zoom out from the mechanics of individual systems, we can map the macro architecture of a complete enterprise data ecosystem. We have 3 specific pillars. The first is the transactional database. Systems like PostgreSQL or SAP HANA process daily operations to answer the question, what is the current state of the business? The second pillar comprises analytical systems like DuckDB or Snowflake, which aggregate massive datasets to answer the question, what historically happened? This architecture diagram introduces the third pillar, the AI knowledge system. Using vector databases, this pillar answers the question, what is conceptually similar? The large language model functions as the reasoning layer, querying these 3 pillars to synthesize a final response. Under this architecture, unstructured assets like design documents, Jira tickets, and meeting transcripts are no longer dark data. They become active, queryable organizational memory. The modern enterprise stack achieves intelligence by augmenting SQL with vector mathematics, providing AI with the precise context it needs to reason accurately about your specific business. Building a semantic memory layer utilizes established relational database logic and commodity hardware. Existing systems like Postgres provide the foundation required to deploy enterprise AI. Because vector search is primarily CPU and RAM-bound, data architects can scale these capabilities using their current cloud or on-premise infrastructure. You can spin up a local Docker container running Qdrant or enable the PG Vector extension in your existing database today. The resources to test semantic retrieval are entirely open source and ready for experimentation. Vector embeddings are the next evolutionary step in database engineering, a mathematical bridge that finally transforms raw, unstructured text into computable meaning.